Welcome to Tales from the Bridge, episode 25. We have Jim Al-Khalili on the show today, one of the most well-known public educators in the world. What a treat it was to hang out with Jim and talk about his science fiction book, Sunfall, and about big science ideas. So we really hope you enjoy this episode. Okay, let's make our way over to the bridge.
Well, we have with us today Jim Al-Khalili. He's a theoretical physicist, an author, and a broadcaster. He's a professor of physics and also a professor of public engagement in science at the University of Surrey in the UK. He is known as an eminent communicator and popularizer of science in the UK and around the world, writing pop science books, presenting TV documentaries, and radio programs on the BBC. That's the British version of our CBC for the Canadians in the audience, where he hosts the Life Scientific, which might be the equivalent of our show Quirks and Quarks on CBC. Is that fair to say, Jim?
Probably close enough, yeah.
So he is also the director of the Leverhulme Quantum Biology Doctoral Training Center, which sounds so awesome. I wish I'd done my PhD there. And I hope we'll get to talk to him about quantum biology later, and also some black holes, FTL drives, and maybe you can tell us what counts as an exotic atomic nucleus. I gather that's your technical expertise. So for the most part, we host authors here on our show, and Jim is the author of many nonfiction books about science, including Quantum, A Guide for the Perplexed, Paradox, The 9 Greatest Enigmas in Science, and The World According to Physics, which I've been listening to this week and is amazing. He's also edited 2 compilations of particular interest to sci-fi fans, What the Future Looks Like, and Aliens, the world's leading scientists on the search for extraterrestrial life. And very recently, he has made his debut into fiction with his own sci-fi techno-thriller called Sunfall, which we really want to talk to you about. So we're really excited to have you on the show, Jim. We want to talk to you about your nonfiction and your science fiction and some science. So welcome.
Thank you very much. Very, very excited to be here.
So why don't we start out with really the most important question, is what type of sci-fi have you been listening to or watching or reading? Anything that you've been reading that you'd like to talk about?
What I've mostly enjoyed in recent years is going through Ian M. Banks' Culture Series books. I realized only recently there were 10 of them, and I looked on my shelf and I only had 6. So I got my kids to buy me the last 4 for my birthday. So I've been working my way through them. So they're just so fun, and he's such a great writer. So very, very escapist.
Yeah. It is escapist. That's the thing about Ian M. Banks, is this future world where humans can just do whatever they want, and it's a techno utopia.
No rules attached. And he doesn't even worry too much about breaking the laws of physics now and again.
Who needs to worry about those when when you've got super powerful sentient AIs and
exactly.
Yeah, we read Accession for the book club a little while ago, so we've discussed it a fair bit. And yeah, what's interesting about his world is the AIs and the robots and the ships. They become so powerful that they're actually the main characters in his books, and the humans kind of get left behind in the dust, right? Like almost like flies on the wall that just happen to be watching.
Yeah, these ship minds are just so much more intelligent. You wonder why humans are still hanging around. Yeah.
He does a good job of anthropomorphizing those minds, to a certain extent. So you feel a certain rapport for them, and you can see their quirkiness and eccentricities. So there's a bit of humanity in those AIs, I think.
Yeah, and also, of course, I guess we'll talk about in my novel Sunfall, I borrow those ideas. Again, I've got sentient AIs, which I call minds. So I hope.
Right.
Well, sadly, Ian Banks isn't with us anymore, so he can't sue me.
Right. Well, that's a pretty good cue. Why don't we just jump right into it? We'd love to talk about Sunfall. Now, unfortunately, usually we come fully prepared and well read, but we couldn't get our hands on your book in time. We couldn't get it on ebook, and I guess the audiobook right now is in Italian. I noticed, but I couldn't find an English one.
Oh,
so
there should be an English one.
There should be one. Okay.
Yeah.
Well, anyway, it's in the mail. It's on our way to us. Now, I've read a lot of reviews, and I'm really interested in talking to you about, the sort of setup for this book, I guess, is the doomsday scenario, is that the Earth's magnetic field has shut off, and so exposing us to both the radiation of space, but also coronal mass ejections from the sun, and hijinks ensue. So maybe you can tell us more about your book, Sunfall.
Well, I mean, I guess I never really set out. It wasn't like, I had the idea fermenting in my brain for years, and finally I've got to get this down on paper. I just finished writing one of my non-fiction books for my publishers, Transworld, and they said, "Oh, what's your next book going to be?" And I said, "Well, I've sort of got everything off my chest. I've talked about quantum physics, I've talked about cosmology, I've talked about the history of science. Maybe I should write a novel next." And they said, "Oh, really? What would it be?" And they sort of caught me off guard. I was like, "Oh, I don't know. I suspect it'll be a sci-fi book, and I suspect it'll be some sort of a page-turner thriller. I grew up on, the sort of the Stephen King type, end each chapter on a cliffhanger, and then it came for him or something, and then you have to turn the page." So I said, well, it'd be probably a page-turner, near-future sort of hard sci-fi thing, which I'd pack with a lot of physics, because after all, that's what I can bring to the table. Right. And they said, fine, go for it. And I realized that it was actually harder than I thought it would be. Writing just fiction is so different from writing nonfiction. But I loved it. I mean, the idea is, you're right, Marty. It's a Earth is in peril, end of the world. Science has to save the day. So it's not like a sort of a Michael Crichton. Science is the villain. Scientists have to come and save the day, of course. But it was pointed out to me very early on that the premise of the Earth's magnetic field shutting down and therefore having to reactivate the Earth's core is not a new idea. And in fact, there's a rather terrible Hollywood movie, The Core, has the same, but I think they have a rocket firing lasers and sort of finding its way to the center. But I wanted to bring in something new. So the idea here is dark matter.
Okay.
And so the story is set 2 decades from now, which for me is a sort of the sweet spot where you can talk about the science that we know today having become technologically sort of commonplace by then. And it's not, you can sort of future scope reasonably reliably and think about what the world might look like. So there's AI, there's augmented reality, there's quantum computers, but most importantly that, we know how to make beams of dark matter, which travel through the Earth. The Earth is transparent to dark matter, but the two protagonists, the heroes, have discovered and won a Nobel Prize for the fact that dark matter interacts with itself. So you get 2 beams of dark matter, as they do in Ghostbusters, don't cross the beams, right? If the beams of dark matter hit, then they annihilate and generate energy. So the idea is you fire lots of beams of dark matter from all around the globe to hit at a single point in the core, very, very precisely, to create enough energy that can kickstart the core. Wow. And then the rest is all goodies versus baddies, and there are these nihilists who want the Earth, feel mankind has destroyed the world, so they want the Earth to magnetic field to die. They want the Earth to go the way of Mars, and the atmosphere gets shredded by coronal mass ejections. So there's that jeopardy that the Earth's magnetic field is now weaker, and we are more exposed to coronal mass ejections and radiation. And I sort of build up. It's almost sort of, at some point, it became almost like Game of Thrones level killing off people. Just when you get to know a character, sorry.
You got to kill your darlings, they say.
Exactly. Right? So it was great fun to write. And while my prose started off very clunky and it was a steep learning curve, what I found I did enjoy doing was the sense of excitement and jeopardy, the page turning, to keep it exciting. So, that Hollywood haven't come to me to make a movie out of it yet, even though I wrote it exactly with that in mind. It was perfect for a movie, but hasn't happened yet.
Well, it might not be long. Yeah. Well, this is. I want to talk to you about that idea, because I have always known, or I guess now it's sort of proven, right, that the Earth's magnetic field really does flip every It says here on the NASA webpage, 200 to 300,000 years.
Yes.
There's been for like 3 billion years, basically, they can track this with core samples of magnetized material that it does flip. It takes 100 or 1,000 years, they say, which is still pretty fast on geological timescales. And so for me, this has always been a very real, and I also gather we're overdue. The last time the poles flipped was 780,000 years ago.
Right.
So,
yes.
So this could happen, in the time span of our civilization. And in my imagining, right, if the poles are flipping, then they must go through zero, presumably, right? And so this would be a time of exposure, and one wonders if it's actually. That would be a great mechanism for punctuated equilibrium in biology, right? You could imagine that there's this built-in time of excess mutations when the magnetic shield comes down. Yep. Although NASA tells me, though, so it turns out that it might be that the pole moves slowly, or it sort of decomposes into multipoles as it's flipping, and then moves. So we might not actually go through that.
It's not one single magnet that sort of turns around. It's sort of, you start to get multipoles and different magnetic field intensities all around the globe. Right, and then they finally coalesce, and you find that the north and south have switched places.
Interesting. So maybe you could just talk more about that. I'm sure you've thought about it a lot. What would happen to us technologically as a civilization in terms of all the electronics that we have, and magnetic guiding? Everybody's compass needle wouldn't work anymore. But what would happen during such a time? Yeah.
Well, certainly, compass needles wouldn't work. A lot of animals, in fact, rely on the Earth's magnetic field for navigation, which was something that in one of my research areas, quantum biology, we're looking into. Mm-hmm. So I sort of brought that sort of research interest into the book as well, that animals have a built-in chemical compass, which we don't really understand the origin of very well, that allows them to be able to follow the direction of the Earth's magnetic field, allow birds to navigate. I think the monarch butterflies that fly down from Canada down to Mexico, they can sense the Earth's magnetic field direction. So the book starts off with a nice truck driver across Alaska who sees monarch butterflies, hitting his windshield, and I think, what are they doing here? And he remembers his daughter's done a project on them at school, and they should be really on the other side of the continent.
Right.
So that sort of thing, I think Earth's magnetic field would affect us. But more importantly is that, as you say, it's a shield that protects us from solar radiation. And so when we get high energy particles coming from the sun, for example, coronal mass ejections, that's how we see the auroras. These particles, high energy particles, hit the molecules of the upper atmosphere, and they become excited, and then they give off light energy. That's that we see that lovely display. That's thanks to the Earth's magnetic field. Of course, without the Earth's magnetic field, those high energy particles would come all the way down to the surface of the Earth, and they would cause havoc with the biosphere, certainly cause havoc with all our telecommunication system, satellites and so on, and as well as frying all the electronics on Earth. So yes, thankfully we have a magnetic field that keeps us safe, and it also keeps the Earth's atmosphere in place, because without a magnetic field, radiation from space would strip away the atmosphere. And that's what many scientists believe happened to Mars, that Mars billions of years ago used to have a magnetic field, and therefore a shield like the bubble wrap that protects its atmosphere, which is why we think Mars could have harbored life. But of course, it's a dead planet now because it has no atmosphere, because it lost its magnetic field for reasons we don't really understand yet.
Right. Wow. Interesting.
So could your antimatter idea of restarting a core, could that be like a terraforming opportunity? Like, could we go to Mars and at some point theoretically in the future when we have the ability to do this and restart the core there?
I mean, are you asking hypothetically in the real world whether we could do this? I mean,
well, you did it in your book. I mean, couldn't that be a trope for a sci-fi terraforming idea?
It's in another sci-fi story. Yes, I guess so. I thought you meant, could we do that in reality?
Well, no, we're trying to work out this. We want to know the sequel here.
Yeah, that's right.
Where you go to Mars.
Thank you. Right, good. Okay, in which case, keep talking. Yeah, because give me some ideas.
Yeah.
Yeah, in principle, why not? Mars has roughly the same density as Earth, as far as I can tell. They're both, rock planets that, it's obviously smaller than the Earth, and so the pressures and temperatures at its core are not as high. But if it did have a magnetic field once upon a time, then that meant it must have had some liquid metallic core that is sort of floating around in the center. In which case, if that's still there, if it hasn't cooled down entirely, then why not use the same technique to kickstart that? But then you'd still have to sort of create an atmosphere. But at least with a magnetic field, you can keep the atmosphere in place.
Right.
That's what people forget when they're terraforming Mars. If it doesn't have a magnetic field, that atmosphere is going to get stripped away again very quickly.
That's what I was thinking.
Yeah, excellent. Good. Thank you. I'm just making notes here.
Well, following on that, I've thinking about, the magnetic field of Earth changing. I've always wondered, are there good models, geophysical models for what's going on in the core? Like, it seems to me to change the magnetic field is meant to come from flowing iron, molten iron core. The iron is sort of carries currents, and so you've got currents running around which generate magnetic fields. But I can't imagine how that, the inertia in that system is so huge. How would the flow inside of molten iron, on the planet size, change? What would cause that to actually make the magnetic poles flip on Earth? Do they have models of that?
I mean, they must do. I'm not a geophysicist, but what I am aware of is that we know surprisingly less than we should do about what's going on in the core of our own planet. You'd think this would be something that's quite an advanced area of science, but we know about sort of eddy currents, and you've got sort of feedback loops of current flowing in a conductor will generate a magnetic field. That magnetic field can induce other currents which interact with the original current, and so you can get all these different complicated sort of feedback effects. But I'm not sure if it's a case, it's like, the currents flow presumably and cycle around because the Earth is spinning. And because they're interacting with the sun's magnetic field as well. I don't think it's a case of the current stopping and starting to flow in the opposite direction, but because that's what I guess that's what I would think as well. How does the magnetic field flip? Well, clearly the currents generating the magnetic field must change direction. I'm very shaky ground here, so I've learned long ago not to pretend I'm an expert in an area and just sort of dig holes for myself.
Well, let me put you on even more shaky ground.
Excellent.
Follow up one more question about the dark matter interacting. I think that's really interesting. I used to, as an undergrad, I got a job at Stanford working on the cryogenic dark matter search. So I built some of those detectors that are now in a mine under Minnesota somewhere, I think. So, I went to I realized that, thinking about dark matter for long enough, that the thing about dark matter is it doesn't interact with regular matter, right? That's why it's there. But you're right. It could interact with itself. And so there could be an entire realm of physics about dark matter interactions. And in fact, who knows? I mean, maybe it's a very structured sort of interaction where there could be dark matter atoms. There could be dark matter molecules. And in fact, there could be dark matter life. Maybe life evolved inside the dark matter realm, and we just don't know it. And we're flying through it all the time, right? It's all around us, and we're just passing through without any access to that. Do you think? What do you know about that? Are dark matter theorists managing to plot out dark matter interactions to figure out if atoms could form?
Well, they certainly can carry out sort of simulations of dark matter on a sort of a galactic scale, and try and understand from the dynamics of stars how the dark matter is distributed, say, within our galaxy. And there are suggestions that the dark matter distribution is not the same as the normal matter distribution. So dark matter, it's more than just gravity. That there is something else that's changing the structure, the distribution of dark matter. So, in fact, a colleague of mine, Justin Reed, who's one of the leading world experts on dark matter, happens to be in the office next door to me. So when I was writing sunfall, I'd pop in and ask him. So if I were to suggest in my book that the leading candidate for dark matter is a supersymmetric particle called the neutralino, would that be crazy? He said, no, the neutralinos haven't been ruled out. We haven't discovered them at CERN or anywhere else yet, but we haven't ruled them out. I said, that's good enough for me. This is fiction, not non-fiction. Therefore, if it hasn't been ruled out, it's allowed. But you're right. It could be that there's this whole new, never mind a whole new world or life created from dark matter, but at least a force that only acts between dark matter particles, whatever they may be made of, that we have not detected because we are not able to interact with dark matter. It doesn't interact with normal matter other than through gravity, which of course is very weak down at the particle scale.
Yeah. So there could be the equivalent of like the strong nuclear force or the weak nuclear force or even electromagnetism in dark matter.
Within dark matter. Yeah.
Interesting.
Ever wondered what it takes to make it in the movie business? Peel back the curtain with 4-6 Success Filmmaking. 4-6 Success Filmmaking is where filmmakers share their stories and the secrets.
It's beyond competitive out there.
There have been movies that it's taken me 10 years to get made.
Don't wait to create. Like, you've got to just keep making stuff.
Tune in to 4-6 Success Filmmaking for your dose of cinematic realness, direct from the voices that have lived it.
Great.
Or a parallel life, like you said, Marty. There's another great science fiction theme, occupying the same space as us, just totally different types of matter.
As a science fiction theme, yeah, absolutely. That would be, I can imagine, the sort of the old guard, the Asimovs and the Fred Hoyles, the hardcore physicists who wrote science fiction. They would take what is possible in the most. To push it to the limit, but all the time it's not breaking any laws of physics. That's the best sort of sci-fi.
Yeah. Well, when I thought of that, when that idea struck me, it occurred to me like that's actually a great metaphor for I guess what people have been calling the spiritual world, right? There could be beings, angels, who knows, right? Like larger intelligences, and in fact, that we're worshipped by, like in the sun, would have the most dark matter in it, right? So actually, the sun would be the planet of dark matter creatures, and we're just this tiny little flake on the.
You're going to get people now sort of commenting on the podcast. Yeah, I knew it. So that's right. Therefore, ghosts do exist.
Exactly. Yeah. That's great. Well, at the end of, so while we're talking about cool physics, black hole physics, and big and small, I read your book, the book you edited called "What the Future Looks Like." Which is a compilation of essays by various world experts about their areas of expertise. It covers the future of our planet, the future of us, as in genetic medicine, things like that, the future online with quantum cryptography and AI, making the future, which is about engineering, transportation, and energy, and then the far future, things like interstellar travel and colonizing the solar system. And then, Jim, you added the last chapter here on teleportation and time travel, where, in the very far future sort of speculative realm, you discuss the possibility of time travel through wormholes ultimately, or through exotic matter that can make frame dragging effects on space-time so that you could travel backwards through time that way. And then you also cover teleportation at the quantum level. About a quantum teleportation, an EPR paradox, the sort of entanglement of two quantum particles giving the ability for instantaneous communication between things that would violate causality, or it would go faster than the speed of light. And so this is the mystery at the core. And then on the very last page, you say some interesting things that I've never heard till now about how there's some new research that suggests a unification of those ideas. Whereas I understood what you said, to solve the paradox of EPR, of instant communication between entangled particles, that perhaps there's actually a wormhole, like a subatomic wormhole, if I understand you correctly, that could facilitate that interaction. And so you could, that's the same idea, that actually it's time travel through a wormhole at the subatomic scale that would allow for instantaneous communication. That blows my mind. That's amazing. Tell me more.
Yeah, so this is actually it's a serious physics idea. It was first proposed less than 10 years ago, and I don't know how much progress has been made in recent years, but it's wonderful because it's built around a lovely story that Einstein published 2 papers in the mid-1930s, completely separate topics. One was on the so-called EPR paradox, Einstein, Podolsky, and Rosen. And it's really Einstein's lament that quantum mechanics doesn't make sense, and he was unhappy with it. He said, if you have, 2 entangled particles very far apart, instantly in communication, well, that's impossible because, I'm telling you guys, nothing goes faster than light, and therefore don't diss relativity theory. And it led to all sorts of, research and is the quantum world really non-local? Do things really act in action at a distance? Well, Einstein hated it. He called it spooky action at a distance. So that was the EPR paper. But within a number of weeks, he published another paper with one of the 2 other authors, Nathan Rosen, where he was also tackling a problem in his own theory of general relativity, where, as to what happens inside a black hole. That there's in the simplest version of general relativity, when a star say collapses to form a black hole, at the center is a singularity, and that's a point of infinite density, infinite curvature of space-time. The laws of physics break down at that singularity, and for Einstein that was like dividing by 0. Just don't do it, right? It's horrible. And so he'd come up with this idea that maybe this center of a black hole isn't a point, it's a tunnel, and it became known as the Einstein-Rosen bridge. And then later on, by the 1980s, people started calling it a wormhole, and that led to sort of all the, the great sci-fi movies and books, like Carl Sagan's Contact, for example. Mm-hmm. And in fact, Carl Sagan's book Contact was written because, I don't know if you know the story, he sent the manuscript to a physicist, Kip Thorne, in California, and said, I'm writing this book about wanting to make connections, links with distant civilizations. Is there a shortcut through space? And Kip Thorne said, yes, you could think about, these wormholes, which are the equivalent of an Einstein-Rosen bridge, which doesn't connect 2 black holes, but maybe doesn't have any event horizons, so you can travel backwards and forwards through it, a Stargate. Carl Sagan said, great, thank you very much. Wrote the book Contact, it became a movie. But that spawned so much more in terms of wormholes. But the idea all goes back to this 1935 paper by Einstein on tackling general relativity. And there's this other paper where he's tackling entanglement in quantum mechanics. So this new idea is referred to as ER equals EPR, where ER are the initials Einstein and Rosen, the general relativity paper, and EPR, Einstein, Podolsky, and Rosen, the authors of the quantum paper. And this idea is that the 2 are connected. Basically, and it's having given you this whole long preamble introduction, the basic idea is actually quite simple, that the reason 2 distant particles are quantum entangled and therefore in sort of instantaneous communication with each other is because they're joined by a quantum wormhole. And within the wormhole,
that is right, yeah, amazing.
The wormhole itself, the Einstein-Rosen bridge, doesn't get any longer. If you take those particles, one over here and the other's the other side of the galaxy, they're still connected by as short a distance as you like via this Einstein-Rosen bridge. And of course, then that means, well, maybe the whole of space and time is weaved together by all these Einstein-Rosen bridges. They connect up all the particles. And it's one of the contenders for a theory of everything. How do you connect the quantum mechanics with gravity and general relativity? I have to say, speaking to sort of quantum gravity experts and cosmologists, not that many of them are as excited as I am about ER equals EPR. And I said, yeah, but wouldn't it be cool? And they say, well, yeah, just because it will be cool doesn't make it right.
Darn it.
But it's such a fantastic, it's still open as to what is the correct theory of everything. Is it string theory? Is it something called loop quantum gravity? Do we have to get rid of quantum mechanics and general relativity and just start again? There are people saying, well, what is more fundamental? Is space fundamental? Is time fundamental? Is it just information? All this stuff is up for grabs because we simply don't know the answer yet. But it would be great if ER equals EPR was right.
Do you think it is something that really mirrors the cosmos to the quantum realm? Or, I mean, will we find a black hole, wormhole in every atom? And is that where we find this connection?
No, I think, in on the cosmic scale, general relativity rules, and you don't have to worry by and large about quantum effects. When you're looking at atoms and subatomic particles, you can ignore gravity. It's so much weaker than the smaller quantum forces, the electromagnetic force and the nuclear forces. You can ignore gravity and just use quantum mechanics. But in principle, they should both apply everywhere on the small scale and the large scale. It's just that because in the different realms, the large and the small, you can take one and ignore the other. It's very hard to find examples where they both manifest themselves very clearly. Maybe, Hawking radiation from a black hole, for example. Mm-hmm. But that's why we have such difficulty. How do we ever do an experiment or make an observation of a phenomenon where both quantum mechanics and general relativity are playing an important role? So we mess around with the maths and have fun with the maths in the meantime.
Right. Well, I think that's why this ER equals EPR is such a powerful idea. For me, it blew my imagination away because I always imagine black holes and wormholes as a large scale, galactic sort of, phenomenon. You don't imagine them at the subatomic scale, but there's this quantum foam, right, at the base of existence where particles and antiparticles pop in and out of existence. And you could actually imagine that that's what a wormhole is, I suppose, right? Like it's a black hole on one side and an anti-black hole or something on the other side.
Because space and time down at that scale are fuzzy. And space-time can take up any sort of shape, bubbles and tubes and knots and so on. So we can imagine that particles popping in and out of existence are somehow connected via these links in space-time itself.
Exactly. Yeah. Like in Feynman diagrams, right? Like these virtual particles that pop in and out are actually an essential thing. You can write it down and how it sort of creates and aids subatomic interactions. So you can I'm imagining now that there's instead of the squiggly line for a photon, right? There's a new line that you could put in the Feynman diagram of a wormhole. Yeah.
Wow.
To mediate subatomic interactions, which is super cool. And anyway, like you were saying, Tristan, right? I think this really is a great idea to link the very large and the very small, right? The wormholes can traverse this entire range of scales to be apparent both at the subatomic level and at the cosmic level. It's beautiful.
Is that what you're filming something right now, Jim? It's called Big and Small? Is that what you're filming?
Yeah.
And are these subjects you're tackling?
Not quite. No, these are the big and small are really the biggest and smallest things we can see. So on the largest, there's 2 episodes. The largest is essentially galaxies and galaxy clusters, and there are these from the supermassive black holes at the center of galaxies spit out these jets, and they create something called Fermi bubbles, which are like the size of a galaxy. So these are the largest structures that we can look at and detect. And then on the smaller scale, we're going down to the level of atoms, but nothing smaller than atoms. Because these are you can actually see an atom, and that blew my mind. Last week I was filming in Germany, and looking down an electron microscope, where the technology has advanced so much that you can actually create an image and say, look, there's the silicon atom, those are the carbon atoms around. Oh, look, it's jumped, and you can watch this fuzzy patch of light that indicates a single atom, and you can watch it moving. So that's the smallest scale. So it's we don't have to go all the way to wormholes to get excited.
Is that the same device in which you shared a photo of yourself? Because I saw the photo of yourself that was in essence smaller than a hair.
Oh yes, that was they're using some sort of ion beam technique, but that's down at the nanoscale. So it's
nano. Okay.
Yeah. So the reason we're making this program is because it's being funded by a Norwegian charity called the Kavli Foundation, and they award prizes, which is what the Norwegians regard as the equivalent of the Nobel Prize, because they're always in competition with Sweden, right? The Scandinavian rivalry. So they give prizes to astrophysics, nanoscience, and neuroscience. So we're covering two of those topics because they're funding this documentary. We're covering the astrophysics subject and the nanoscience subject. So the small is all the nano stuff, all the way down to atoms.
Cool.
Cool. Well, since we're talking about advanced technology, I mean, the part of the point of this book, the what the future looks like, was to sort of take real science that definitely exists today that we understand and extrapolate forward into the future to see how it might play out. And you've done this in your sci-fi book, and this is obviously a theme that science fiction is generally built upon. So I'm wondering if you wanted to speculate for us in your chapter here was on the very far future. So maybe you could speculate on the near future of what you see as the most transformational technology that will come about, maybe in our lifetime, maybe say in 100 years, that could really change the world or save the world even, right? Like what is the enabling technology, I guess, that you're most excited about?
I think undoubtedly the thing that's going to change our world is AI. Artificial intelligence, whether we reach at artificial general intelligence, where AIs become as intelligent as us, they become sentient. I don't know whether that'll happen in our lifetimes, but I'm not in really much doubt that it's coming. There will come a time when machines will be smarter than us, and I think the important thing now is that we have, as a society, have the debates and discussions about the ethics and implications of this. In the short term, it's all about automation and robotics, using AIs to help us, whether you're detecting cancer tumors or whether, the pattern recognition stuff, whether you're sort of filtering information online, from fake news, from what is true, or whether it's used as a marketing tool for, as we know already, when you go onto Netflix and it says, you might like to watch this film, and think, wow, yeah, I would actually. How do you know? Well, of course, that's easy enough. The AI is monitoring what you're watching. So I think that's the immediate future. And also, the fact that our jobs are going to change in the next 10, 20 years because AI and automation and robotics is going to take over a lot of roles that humans are doing. We've had this since the Industrial Revolution, right? Steam and machines, the plow. We've always used machines to do jobs to make our lives easier. We no longer have to wash things by hand. We've got a washing machine. This is the next step, but it's using electronics. And that's exciting, but it's sort of inevitable. What people aren't talking about enough is future AI, when AI becomes so powerful, so intelligent, that it is self-aware. It's not going to think like a human. Why should it? It's not going to be designed like a human brain, nor will it have the millions of years of evolution that have made us the way we are and think the way we do. But there's no reason why an AI wouldn't one day feel emotions, whether it's anger or happiness or envy or whatever. That's not something unique to biological life. It's not like, our brains are just, neural connections that we sprinkle pixie dust on and suddenly we become self-aware. So it's going to happen. And we try not to talk about the Terminator scenario that, sort of the machines will take over the world and render us obsolete. But it's still something we should be talking about, because I think more than anything else, more than quantum computers, more than virtual reality, augmented reality, or, I think AI is the thing that's going to change our world in the 21st century. Assuming we can use it then to solve other problems. Maybe AI can help us solve, the climate crisis, for example. Mm-hmm. So it's very important, not just because it's fun or it's a threat, but because we can maybe actually use it to tackle the challenges that we humans haven't been able to figure out how to do yet. Maybe AI can help us.
So when you say the ethical implications of that, are you thinking if you have a sentient AI that that it should be treated as a sentient AI. Is that what you're talking about?
Yeah, both in terms of the ethics of how we want it to treat us and how we have to have in place, whether it's Asimov's three laws or something equivalent to that we still want to be in charge, right? This is our planet. Don't decide that you can dispense with humans just because you're smarter than us. But you're right, absolutely. If a machine is sentient, we have the debate now about whether or not are animals sentient? Yes, of course they are. Can they feel pain? Yes, of course they can. That's why so many people are becoming vegetarians and vegans, and that's why we don't like seeing a whale washed up against the shore. So we know animals are sentient. AIs would be sentient as well, and we have to think. You can't just reach to the off button on a AI computer and flick it off, as has been explored, I think, already in lots of science fiction.
Mm-hmm. Oh, for sure. Well, we actually had this conversation with Peter Watts recently. He's a Canadian science fiction author, and he's a biologist. And so he had some surprising ideas and insights about exactly what you said, that why shouldn't AI have emotions? Well, emotions evolved as a survival response, right? Biologically, to exert pain or exert fear for flight or flight. Like there's a very large biological literature about how emotion evolves, but as a function of survival, right? And so it actually raises an interesting set of questions for AI. Can you just program it in emotions or even sentience, right? The sentience arises from emotions, and even the scenario we worry about is that the AI decides it's threatened and doesn't want to be turned off because it wants to survive. And so this is the question: does it want to survive, and how do you program that in? And maybe that's something that can only evolve in a biological context, this sort of need to survive and then emotions with it. And so anyway, for me, that sort of eased my mind a little bit, that I don't quite believe that just programming more and more complicated things into a computer will one day make it become self-aware.
No,
it is a uniquely biological result.
Well, I don't. By biological, we simply mean because subject to Darwinian evolution, and that's mutations and changes and things evolve by accident and survival of the fittest, and it's a slow process. So I guess what you mean by it's a uniquely biological process, you mean it's very slow and therefore it's not going to happen quickly. But I don't see any difference. The laws of physics and chemistry don't work differently in biological systems when compared with electronic systems, for example. And so it wouldn't be the case that we as humans are coding ever more complicated programs and instructions into a machine that the machine will learn. I mean, the current AI algorithms are all about machine learning. You just give it a simple set of rules and it will play them again and again and again and teach itself. That's how AIs get so good at playing chess or the Chinese game of Go or 1980s Atari video games or whatever it is that they try these AIs out on. You're not telling them what to do. You're not teaching them. They're teaching themselves. And so I think with machine learning, they will do the equivalent of Darwinian evolution in biological systems, only much, much more quickly.
Right.
So what I'm saying is, don't feel reassured.
Right.
that I don't see any logical argument against machines being able to evolve, whether they're evolving just logical problem-solving skills or sentience or emotions, that couldn't happen just naturally, but much more quickly than it's happened in life forms.
Right. Yeah. So it's actually the opposite. Like you said, don't be reassured, because maybe the fundamental principle that needs to be at the core of this evolutionary process to create sentience is the desire to survive, right? So maybe that will be ultimately at the core of any sentient or powerful AI.
Yeah, and it may emerge. That's what it may emerge rather than being an instruction that we put or not put in.
Yeah, and then it could be threatened, right? And maybe it will seem like, whoa, these guys could turn me off. I better stop that.
Yeah, exactly.
Yeah. So quantum biology is kind of what I really wanted to do when I got into physics. I mean, I was raised on slightly more flaky pop physics books than you write. I think I gotta admit to you, Fritjof Capra's The Tao of Physics
Oh yeah,
was the inspiration for me to get into physics, because I was this philosophical kid meditating in the woods.
You
And, somebody
hippie.
told me,
Yeah.
I'm the mystic here. I'm not even a really hard science guy. But also Roger Penrose's book, The Emperor's New Mind.
Yes,
So
yeah,
he
absolutely.
proposed this crazy idea at the time, and it's probably still a crazy idea, right? That the consciousness is ultimately a
and
quantum
yes.
phenomenon. And he was working with this guy,
Hammeroff.
Hammeroff, thank you.
Yeah.
Who suggested it's in the mitochondria or their specific organelles, right? That the actin, I think it was, the microtubules.
Microtubules in the neurons, yes.
Yeah, we're
Tubulin.
quantum computing, right? There's these quantum states in there that could arise. Now, now Roger Penrose has won a Nobel Prize since that time for his work on quasicrystals. So now he's a very respectable scientist, and I'm a. Maybe you could just comment on that. Is that the level, or is that the kind of thing that you're examining with quantum biology, or is it more about rhodopsin?
It's somewhere in between. That sort of woo-woo quantum mechanics explains everything. Oh, well, consciousness and therefore quantum mechanics explains telepathy and homeopathy and all the other crazy nonsense.
Sure.
But it's also more than just, well, of course, biological systems are made of atoms and atoms behave quantum mechanically. Therefore, quantum mechanics has to be at the base of biology. That's taken as a given. It's not interesting, because inanimate matter equally is made of the same atoms as animate matter. So why should it be different? No, this is it's exciting, because what we're looking at is specific mechanisms, phenomena, stuff that goes on inside living cells that couldn't happen so efficiently that's necessary for life without a helping hand from quantum mechanics. So, for example, the area that we're working on now, and in fact, I had a meeting with one of my grad students this morning about a paper we're just submitting in DNA. The two strands of DNA in the double helix, they're held together by hydrogen bonds, which is basically a hydrogen atom. Or in my case, because I'm a nuclear physicist, I don't care about electrons, so it's just a proton. All right, that's all I care about. It's a proton that provides the glue between the two strands of DNA. Mm-hmm. And those protons can jump from one side to the other. They can hop. And that was even going back to sort of Crick and Watson in the 50s. They had proposed that could be possible. So what we're doing now is these very sophisticated quantum calculations to see how likely it is that a proton will jump from one side to the other. Because if it does and finds itself on the wrong side, then as those two strands of DNA get unzipped inside an enzyme called the helicase, which splits the strands of DNA and then makes copies of them. That's how cells replicate. If that proton's on the wrong side, on the wrong strand when they split, that will lead to a mutation when the strands make copies of themselves. So the question is, succinctly put, do mutations in DNA depend on quantum tunneling of protons? And it turns out that that's a very important effect. Yeah. So it's things like that. It's quantum mechanics. It's non-trivial quantum mechanics that doesn't take place in inanimate matter of the equivalent complexity. This is happening inside DNA, that underpins some feature of life. And there are other examples, like, in photosynthesis, the photon of light captured, the photon of sunlight captured by chlorophyll is delivered down to the center of the cell by following multiple paths simultaneously, which in the quantum world we're used to. That's what the famous two-slit experiment in quantum mechanics is all about, particles going in two directions at once. This is happening inside cells of plants and bacteria to generate photosynthesis, generate energy from sunlight. So there are examples like this which are down at the molecular scale, very difficult calculations to do, even more difficult experiments to test those theories. But if they're right, they're very, very exciting. It may be that they're not, but so far it looks like there's some interesting stuff, and it's bringing in theoretical physicists, computational chemists, molecular biologists, even philosophers to understand the implications of this. It's a new field, and it's good to be in it from the beginning.
It's really exciting. Yeah.
Do you know Stuart Kaufman? Have you heard of him?
Yes. Yeah.
I read all of his stuff. I think he's a really fascinating thinker in this realm, right? Like where he talks about, I mean, what I'd like to know about from what comes out of this quantum biology is what are the new powers or capabilities, right? That maybe biology is granted by these effects. And so he has a really he sort of thinks about quantum mechanics, but sort of at a biochemical level where the sort of tunneling to the adjacent possible, I think he calls it, right, in terms of the complexity of possible configurations of amino acids to get together to are actually linked in some sort of quantum mechanical superposition because there's so many of them and they're displaced so little in energy, and then there might be an actual sort of topography to those pathways that then life can manage to navigate in a way that's not just a random walk.
So we cover this in. So I wrote a book, Life on the Edge, with colleague John Joe McFadden, and we cover exactly some of these ideas. We start off with what the quantum biology that we're quite comfortable with. Enzymes moving atoms around using quantum mechanics. Yeah, that's pretty well established. All the way to, did quantum mechanics play a role in kickstarting life in the first place, because it was such an unlikely thing to happen? And also the Penrose hammer of, is quantum mechanics the underpinning consciousness? By that point, it's speculation. It's not. We're not saying we're so far. We want to walk before we can run. So we say, look, this is very speculative, but very exciting if true. Paul Davies is another physicist at Arizona State University who's talked about a lot of this stuff and whether it's possible. So yeah, it's exciting, and we just have to wait and see if what comes of it and where it takes us. The sexy bit is things like, I mentioned earlier in Sunfall with the monarch butterflies migrating. The European robin does the same thing. It can sense the Earth's magnetic field. It could be that the compass that these creatures have is in a protein in their eye called cryptochrome, which is activated by light. And you have two quantum entangled electrons, right? We're back to Einstein, Podolsky, Rosen entangled particles. The particle of light splits those two electrons apart. They're still quantum entangled, but the way they move relative to each other is sensitive to the orientation of the bird in the magnetic field. So basically, Einstein's spooky entanglement that he didn't like could be a quantum biology candidate that helps birds and butterflies and other marine mammals navigate around the world. It's lovely. It links in so many different ideas. And again, it's one of those things.
Wormholes.
And wormholes. I mean, I hope it's right, but that's not good science. You don't do science by saying, this is such a cool idea, it better be right. You have to try it out. And you have to be prepared to say, no, it was a load of nonsense.
Right.
Yeah, but that's how you do science fiction books.
I gotta say, exactly.
Cryptochrome is like the coolest sounding book title I've ever heard.
Or a band name.
Or band name.
Yeah.
That's great. Cosmic strings. What are cosmic strings? I sort of left the world of understanding. Where does that come from?
I think the idea has gone a little bit out of favor now. You may not have picked the right final topic to cover here. Certainly, in the 80s, I guess, in the 90s, the idea is that, at the Big Bang, all sorts of space-time structures and matter distributions could have formed. Cosmic strings they could stretch for many, many light years across the universe. They're infinitely thin strings of material or exotic matter. We've seen no evidence of them, and I think they are predicted by certain theories in cosmology and quantum gravity. But I think they're sort of out of favor now, in the same way that idea of faster than light particle tachyons went out of favor. They have their day. They become very fashionable among theoretical physicists, and then they realize that there's no evidence for them, and it maybe our theory is wrong, and they move on to something else. Okay. So you don't hear people talking about cosmic strings much these days.
Well, if tachyons aren't going faster than light, how are we going to get going faster than light, Jim? Tell us.
Yeah, well, that's the big question. I mean, wormholes is a possibility, but wormholes requires a particular manipulation of space-time. Sort of mass and gravity and exotic matter. And I guess faster than light travel also requires some sort of exotic matter. I think the usual idea that sort of superseded Star Trek's dilithium crystals was that warp drive is about scrunching up space in front of you and stretching it out behind you. It's a bit like pulling a carpet, a rug underneath you, so you can jump across a larger distance, and then you can stretch it back again behind you. Very speculative, these ideas. I mean, if I were a betting man, I'd say no, faster than light travel is not possible. According to our current ideas in physics, and general relativity basically is our best theory of the nature of space and time. But who knows whether general relativity is the last word on the subject, and who knows whether 100 years, 200 years from now, we go, we were so dumb to think, or so unimaginative to think that faster light travel was impossible. But certainly traveling through normal space without scrunching it up or stretching it or warping it, you cannot go faster than light. That leads to paradoxes of causality and all sorts of weird nonsense that we can say, okay, there we're safe. But exotic shapes of space-time, well, all bets are off.
Great.
So, well, just being at the in the holiday season here, are you saying Santa can't do this? If there was a device that he uses, can you kind of tell us what that device looks like for him to visit every home?
Well, he clearly does, and he clearly has figured out the technology. We're just a bit way behind Santa. Okay. So he maybe he uses a wormhole, maybe he warps space-time in some exotic way. Maybe he's found a way to defeat faster than light travel through normal space, and Einstein will be turning in his grave. But clearly Santa does it somehow. If only we knew how.
Well, this of course raises the possibility that Santa is an advanced technological alien from another civilization.
That may well be the only solution.
Probable.
Yeah.
Great. Well, it's been a real pleasure talking to you. Thank you so much for coming on the show. We'd love to talk. I've got a list of more science questions.
Have me back for part 2 sometime.
We would love to.
I've enjoyed this.
Well, we'll read Sunfall, and then we'll have you back for that.
Let me know what you think.
For sure. Yeah.
Great. Okay.
Great. Thanks very much, guys.
Thank you, Jim. That was awesome. So fun to have Jim on the show. He's such a cool guy. We really look forward to talking to him again, especially after we read Sunfall. Really looking forward to that. Okay, next episode we are talking about Ancestral Night by Elizabeth Bear. We hope you can join us for that. Until next time.